Einstein's special theory of relativity is a fundamental theory that has changed our understanding of the universe. It was first introduced by Albert Einstein in 1905 and is based on two simple principles: the constancy of the speed of light and the principle of relativity. In this video, we will explore the concepts of time dilation, length contraction, and the equivalence of mass and energy in more detail. In the late 19th century, scientists had developed a detailed understanding of the behavior of light and its wave-like properties. However, their attempts to explain the nature of light and its propagation through space led to a fundamental problem. They believed that light waves traveled through a medium called the ether, which was thought to permeate all of space. However, experiments designed to measure the speed of light in this ether failed, leading to a crisis in physics. The failure of these experiments led many scientists to conclude that the concept of the ether was flawed and that a new theory was needed to explain the behavior of light. This was the starting point for Einstein's special theory of relativity. Einstein's theory proposed a radical new way of thinking about space and time, which would transform our understanding of the universe. Einstein's theory challenged the fundamental assumption that space and time were separate and absolute. Instead, he proposed that they were intimately linked and that the speed of light was a fundamental constant that was the same for all observers, regardless of their relative motion. This was a radical departure from the prevailing view of the time and required a complete rethinking of our understanding of space and time. Einstein's theory was based on a few simple postulates. The first postulate was that the laws of physics are the same for all observers in uniform motion relative to each other. This meant that the physical laws that govern the behavior of objects, such as the laws of gravity and electromagnetism, would be the same for all observers in motion. The second postulate was that the speed of light is constant and is the same for all observers, regardless of their relative motion. Einstein's theory also introduced the concept of time dilation. This means that time appears to slow down for objects that are moving at high speeds relative to an observer. This effect has been observed in experiments using atomic clocks that have been flown in airplanes and satellites. The clocks that have traveled at high speeds have been found to be slightly behind clocks that have remained on Earth. Another consequence of special relativity is the phenomenon of length contraction. Objects that are moving at high speeds appear to be shorter in the direction of their motion when observed by an observer at rest. This effect has also been observed in experiments, such as with high-energy particles traveling at close to the speed of light. Time dilation is a crucial aspect of special relativity, and its implications can be quite startling. According to the theory, time can appear to move slower or faster depending on the observer's relative motion. This means that time is not an absolute concept, but rather a relative one. This can be difficult to grasp, as we are used to thinking of time as a constant and unchanging aspect of the universe. To understand time dilation, let's consider an example. Imagine two identical clocks, one on Earth and one on a spaceship traveling at a speed close to that of light. According to special relativity, time will appear to pass more slowly on the spaceship relative to Earth. This means that the clock on the spaceship will appear to be ticking more slowly than the clock on Earth. This effect has been observed in many experiments, including the famous Haffel-Keating experiment in 1971. In this experiment, atomic clocks were flown around the world on airplanes, and it was found that the clocks on the planes ran slower than stationary clocks on Earth. This is exactly what special relativity predicts. Time dilation has important implications for our understanding of the universe. For example, it helps to explain why high-energy particles such as cosmic rays can reach Earth from distant sources. These particles are traveling at very high speeds, and as a result, time appears to pass more slowly for them relative to stationary observers on Earth. This means that from the particle's perspective, it can travel much farther in a given amount of time than it would appear to from Earth. Time dilation also has practical implications. For example, it plays a role in the functioning of the Global Positioning System, GPS. GPS relies on precise timing measurements to determine the location of a device on Earth. However, because satellites in the GPS system are traveling at high speeds relative to Earth, time dilation causes their onboard clocks to run slower. Without taking this into account, GPS measurements would be inaccurate by several kilometers. According to special relativity, as an object moves closer to the speed of light, its length appears to decrease when measured by an observer who is at rest relative to the object. This means that the object would appear to be shorter in the direction of its motion than when it is at rest. The effect is not noticeable at everyday speeds, but it becomes more significant as the object's velocity approaches the speed of light. To understand length contraction, imagine a spaceship traveling at a high velocity relative to an observer on Earth. From the perspective of the observer, the length of the spaceship appears to be shorter than its actual length when it is at rest. This is because the time it takes for light to travel from the front of the spaceship to the back is longer than the time it takes for light to travel from the back of the spaceship to the front. Therefore, the observer sees the spaceship as contracted in the direction of its motion. Length contraction has important implications for our understanding of the nature of space. It means that space itself is not fixed and absolute, but it is relative to the observer's motion. This challenges the classical view of space as a fixed and absolute entity and opens up new avenues of research in physics. The phenomenon of length contraction has also been confirmed by many experiments, including the famous Michelson-Morley experiment, which tested the properties of light and the hypothetical ether. The results of this experiment confirmed the validity of special relativity and led to a new understanding of the nature of space and time. Einstein's equation, E equals mc squared, expresses the idea that mass and energy are interchangeable. It shows that a small amount of mass can be converted into a large amount of energy and vice versa. This was a groundbreaking idea and has important implications for nuclear energy. The equation shows that even small amounts of matter contain an enormous amount of energy. This is because the speed of light is a very large number, so when it is squared and multiplied by a small amount of mass, the resulting amount of energy is huge. This is the principle behind nuclear energy, where small amounts of matter are converted into enormous amounts of energy. The equation helps to explain the energy released in nuclear reactions, which powers the stars and drives many other processes in the universe. It also provides a link between mass and energy, which is crucial for understanding the behavior of objects in the universe. In addition to its scientific significance, Einstein's equation has also captured the popular imagination. It is often used in popular culture as a symbol of the power of science and the mysteries of the universe. Its simplicity and elegance have made it one of the most famous equations in history, and it continues to inspire scientists and the general public alike. The idea that nothing can travel faster than the speed of light is a fundamental concept in special relativity. This concept is so important that it has been referred to as the speed limit of the universe. According to special relativity, the speed of light is a constant that is the same for all observers, regardless of their relative motion. This means that no matter how fast an object is traveling, it can never exceed the speed of light. The speed limit of the universe means that there are limits to how fast we can travel through space and how quickly we can communicate with distant objects. This has led to the development of technologies like radio telescopes and space probes that allow us to study the universe at great distances. The speed limit of the universe also has implications for our understanding of the nature of black holes. Black holes are objects with such strong gravitational fields that nothing, not even light, can escape from them. This means that anything that enters a black hole is effectively lost forever. The speed limit of the universe is a key factor in the formation and behavior of black holes, and it has helped us to understand the extreme conditions that exist in these objects. In addition to GPS systems, special relativity has had numerous other practical applications. The understanding of time dilation has been applied in the development of particle accelerators, which use the effects of time dilation to achieve high energies in small spaces. The principles of special relativity have also been used in the development of nuclear power and nuclear weapons, as they rely on the equivalence of mass and energy. Special relativity has also had an impact on our understanding of the behavior of matter and energy in extreme conditions. It has been used to study the behavior of particles at high energies, such as those in particle accelerators or during the early stages of the universe. Special relativity has also been used to understand the behavior of black holes and the gravitational waves they emit. In addition to its practical applications, special relativity has had a profound impact on our understanding of the nature of the universe. It has challenged our common-sense notions of space and time and has shown us that the universe is far stranger and more complex than we ever imagined. It has inspired generations of physicists to explore the nature of the universe and to push the boundaries of our understanding. In conclusion, Einstein's special theory of relativity is one of the most revolutionary ideas in modern physics. It has completely transformed our understanding of space and time, and has had important implications for our understanding of the universe. The principle of relativity and the constancy of the speed of light have challenged our intuitions about the nature of reality, but they have also helped us to understand the behavior of matter and energy in extreme conditions. Time dilation and length contraction have been confirmed by numerous experiments and have important implications for our understanding of time and space. The equivalence of mass and energy has led to important advances in nuclear energy, and it has helped us to understand the behavior of matter and energy in extreme conditions. Finally, the idea that nothing can travel faster than the speed of light has helped us to understand the behavior of matter and energy in extreme conditions, and has led to many practical applications, including the development of GPS systems. Overall, Einstein's special theory of relativity has transformed our understanding of the universe and has had important implications for both our theoretical understanding and our practical applications. It is a truly remarkable achievement, and it will continue to be an important area of study for many years to come. Thank you for watching. Please don't forget to like and subscribe and share the video with your friends.